Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last lecture we had started to discuss about traffic assignment problems. So, let us continue the discussion here. In the last lecture we had seen that we can solve the traffic assignment problem, especially user equilibrium, when the example network is very small graphically, but that may not be possible if the example that is given is more complex, and that is because of the following reasons. For instance, there could be large number of paths between any given origin to destination pair. So, even enumerating all of those paths may not be an easy task. Okay. Similarly, there can be multiple origin destination pairs. So, until now in the examples that we had looked at, we had only considered a single origin destination pair, but when there are multiple origin destination pairs or OD pairs, then we need to take into account the flows that are being passed from one origin to different destination. Okay. So, therefore, if we are trying to determine the flow through a particular link, then we need to sum up the flow which is happening across all the OD pairs from that link. Okay. So, that may not be very easy when there are many OD pairs and the network is complex. There might be many overlapping paths between different origin destination pairs and so on. Therefore, we need systematic methods to determine user equilibrium when the problem is complex. So, fortunately, the user equilibrium problem can be formulated as an optimization problem. So, we will be seeing that sometime later, but before that we will be going through some of the important concepts of optimization. Now, as we have seen that in the traffic assignment problem, especially user equilibrium, here the link flows, path flows and so on are allowed to be continuous values. So, therefore, this user equilibrium problem can be formulated as a continuous optimization problem, which we will be going to see later. But since it will be a continuous optimization problem, unlike the most of the discrete optimization problems that we had seen before, a lot of concepts related to how to solve these problems and so on change. Okay. So, let us go through some of the important concepts and theory of continuous optimization problems. So, just to quickly recap what does a general optimization problem contains. So, we know that there is always an objective function. So, this is a single quantity that needs to be either maximized or minimized. Similarly, we will have decision variables. Okay. So, these will be the variables that we can control in order to achieve the objective that we have. And then we can also have constraints. Okay. So, these constraints will represent different restrictions on the decision variables that must be obeyed. Okay. Note that every optimization problem will always have an objective function and decision variables, but it may or may not have constraints. For the case when we do not have constraints in an optimization problem, it is called unconstrained optimization, and when we have constraints, it is called constrained optimization problem. Okay. So, let us quickly take a look at an example of a continuous optimization problem. So, suppose we have a function z that is a function of two variables x1 and x2 here. Okay. So, we have these two constraints here, x1 plus 2 x2 is greater than or equal to 2 and x1 is greater than or equal to 2. Now, we have discussed this before also, that every minimization problem can be converted to an equivalent maximization problem. So, therefore, whatever concepts that we will be focusing in the subsequent discussions, that will be focused on minimization problems, but all of them can be extended for maximization problems as well. So, just to remind, I mean, if we have an optimization problem which is maximizing this function z, so this is equivalent to saying that we want to minimize the function minus z. Okay. And we can consider this function minus z as a new function z dash. Okay. Okay, and the set of all the possible values of x1 till xi that satisfy all the constraints is called the feasible region. Okay. So, this also we know. So, if we have capital I decision variables, so all the possible values that these decision variables take and they satisfy all of these constraints, then that all those possible values are called the feasible region. Okay. So, this is one way of representing the feasible region for general optimization problem, specifically continuous optimization problem. So, we have these capital J constraints here. This is the first constraint, then the second, and so on. So here B1, B2 till Bj are constants, and G1, G2, Gj are functions which are varying with x1, x2 till capital Xi. Okay, so let us represent this vector x1 till xi by this bold x here. So therefore, a general minimization problem can be written as follows. So we are minimizing this function zx subject to these constraints here. So we have capital J constraints. So the solution of the above program is x star, that is the optimal solution is x star, provided that the objective function value at x star is less than or equal to the objective function value at any feasible x, subject to that this x star satisfies the constraints that we have. Okay, so all of this we have seen before, but we are just quickly recapping. So this is just the standard definition of an optimal solution. Okay, so this is just an example optimization problem. Suppose we have two constraints that x has to be greater than or equal to a and x has to be less than or equal to b. So the solution is restricted in this region here, and suppose we want to minimize the function z. Okay, so then the optimization problem will be written like this. It will be minimize this function z, which is just varying with one variable x, such that x is greater than or equal to a and x is less than or equal to b. Now this constraint x less than or equal to b is equivalent as minus x greater than or equal to minus b. Okay, so now both of these two constraints are in this form here, where we have these greater than or equal to sign. So here the g1 constraint is this function x here, g2 is minus x here, and b1 is a here, and b2 is minus b here. Okay. So general minimization program can be written as this is the objective function z, which is a function of capital I decision variables subject to these constraints. So we have a total of capital J constraints. Okay, so this is the case of continuous optimization problem. Now you must be wondering that why we just have these kind of constraints where we have greater than or equal to. The reason is that we can convert other type of constraints also to this form. For example, if you suppose have an equality constraint, suppose x is equal to a, okay, then this is equivalent to saying that x is greater than or equal to a and x is less than or equal to a. Okay, now this constraint is already in this form that we want, but in order to convert this constraint, we will multiply by minus 1 on both the sides, and now this one is also in this form where we have this greater than or equal to. Okay, so these variables x1 till x capital I are the decision variables here. So we have a total of capital I variables. So in the unconstrained minimization problems, we do not have any constraints. So then the problem is just to minimize this function zx. Okay, now we will be assuming that this function zx is continuous and differentiable. Okay, so this would not have been possible if we were working in the domain of discrete optimization. So that is why now we are in the realm of continuous optimization problem, and whatever we will be presenting next will be based on these assumptions here. Okay, now let us first focus on the case when there is a single variable, that is this vector x is just equal to one variable x here. Now a necessary condition for this function zx to be minimum at x star is that the derivative of this function z should be equal to 0 at x equal to x star. Now many of you might have already seen this equation. Okay, now you must definitely try to think, what does this physically mean? This means that the slope of this function z at x equal to x star is equal to 0. Okay, so this is a necessary condition. So what does that mean? That if the x star is the optimal solution for zx, then dz by dx has to be equal to 0. Okay, but the reverse is not true, that is, it does not necessarily mean that if dz by dx is equal to 0 at x equal to x star, then x equal to x star will be a minimum always. Okay. So, this is known as the first order condition for a minimum. Why first order? Because we have this first derivative with respect to z to be equal to 0 at x equal to x star. Now, as I said that this condition is a necessary condition. Okay. So, it does not mean that if the slope of a function at a point x star is equal to 0, then that point will be minimum. For example, if you look at this function here, there are these 4 points where the slope is going to 0. Okay. But then there can only be one minimum or a global minimum, okay, of this function. So, suppose that in this direction the function will be always increasing like this, and in this direction it will always be increasing like this, then the minimum will be at A. Okay. Even though there are 3 other points where B, C and D where the slope of this function is 0. Okay. So, all of these points A, B, C and D where the slope of this function is 0 are called the stationary points. So, a minimum will have to be a stationary point if we are looking at this unconstrained optimization, that is, we are just minimizing this function zx here. Okay. And right now we are considering the case of single variable here. Okay. But not all the stationary points need to be minimum. For example, out of A, B, C and D there is a single minimum which is at A. Okay. So, that is why it is a necessary condition and not necessary and sufficient condition. Okay. So, this is saying the same thing, A, B, C and D are all stationary points because at these points the slope of the function is equal to 0. Now, out of these A, B, C and D, A and D are local minima. Okay, what does local minima mean? That if you take a very small region around a particular point, then at that point the function value will be the minimum. Okay, so you can see that around this region here the minimum value occurs at A. Similarly, around this point D, the value that is taken by the function is minimum. Okay. Then there are some points which are local maximum. Okay. So, C is a local maximum, because if you take a very small region around this point, the function value takes the highest value at this point. Okay. And those stationary points which are neither local minimum neither local maximum, they are called inflection points, like this point B here. So, this is neither a local minimum neither a local maximum. Okay. Now, the big question here is that how to determine if a stationary point is a minimum. So, we have seen here that not all the stationary points need to be the minimum. Okay. Whenever I will say minimum in this course, I automatically mean that it is a global minimum that I am referring to. Okay. So, we want to find a point A which has the lowest value among all the points. Okay. Okay. To ensure a stationary point is a minimum, one thing is that it should first be a local minimum. Okay. That is, it should neither be a local maximum nor an inflection point. And among all the local minimum, it should be the one where the function value is the lowest, that is, it should be the global minimum. Okay. This is what it is saying, that is, it is the lowest among all the local minima. So, in order to understand these conditions here, we will be introducing the concepts of convexity and strict convexity. These are very important concepts. So, a function is said to be convex if the line segment between any 2 points of the function does not lie below the function between the 2 points. Okay. Just take a look at this definition for a moment here, and then we will be trying to understand this from some examples, and we will be also trying to see what does it mean mathematically. So, again, a function is said to be convex if the line segment between any 2 points on this function does not lie below the function between the 2 points. So, to understand this, let us take this diagram here. Suppose we have arbitrarily picked any 2 points in this function, suppose x1 and x2. Okay. Okay. So, the points on the function are at these values x1 and x2 are A and B. Okay. Now, mathematically this condition that this function z is convex means that if you draw a line segment which connects these 2 points A and B here, which is this line segment here. So, this line segment will never go below the corresponding point on the function. Okay. So suppose you look at any point on this line segment, suppose you pick a point this C here. Now you will see that this point C will never lie below the corresponding point on this function, which is this point D here. So this C you can see is not lying below the point D here. Okay. So how to write this mathematically? So this is x1 here, this is x2 here. So let us have this parameter theta which takes the value between 0 and 1. So theta x1 plus 1 minus theta x2 is suppose this value here. Okay. So how close is this value to x1 as compared to x2 will be dependent on the value of theta. Okay. So if theta is very small, then it will be closer to x2. If theta is very large, then it will be the other way around. Okay. So at this value theta x1 plus 1 minus theta x2, the value of the objective function is z times theta x1 plus 1 minus theta x2, okay, which is this thing which is written in the left hand side here. Now what is the value here at this point C, which is lying on this line segment and exactly on the same vertical line here as this point D. So since the objective function value at this point A is zx1 and the one at point B is zx2 here, so the value at this point C is theta times zx1 plus 1 minus theta times zx2. Okay. So now you can see that it is saying that the function value at this point D, which is z theta x1 plus 1 minus theta x2, which is this quantity on the left hand side, is always less than or equal to theta times zx1 plus 1 minus theta times zx2, which is this point here. Okay. So this is saying the same thing. So this point C has a value theta times zx1 plus 1 minus theta times zx2, and the point D has a value z times of theta x1 plus 1 minus theta times x2. Okay. Now let us take a look at some of the examples of convex functions. These are some examples here. To understand intuitively, let us plot these functions here. So this is the diagram of this function zx equal to x square. So you can see that if you pick any two arbitrary points here, suppose you pick this point here and suppose you pick this point here, and you suppose connect them through a dashed straight line here. Okay. So you will always see that this dashed line segment will never lie below the corresponding point on the function. Okay. Suppose you choose this point arbitrarily on this function here, and suppose you drop a vertical. So this is that point which is directly below. Suppose this is this point C here and this is this point D here, where this vertical has dropped on this function here. So you will see that C will never be lying below this point D here. Okay. Similarly, this function zx equal to e to the power x. Again, you can see that if you pick any two arbitrary points on this function, suppose this and this here. So let us label them as A and B here, and suppose you join them through a dashed line segment here. So then any point on this dashed line segment, suppose this point C, this will never go below the corresponding point on the function. So again, let us drop a vertical line segment here, and this is suppose the point where it strikes this function here. So you will see that this point C is not below this point D here. Now this function is very interesting, zx equal to 2x plus 3 here. This is a straight line here. So now if you suppose pick any two arbitrary points, suppose this is a point A here, this is a point B here. Now you notice that any line segment which connects these 2 points A and B is actually this line itself. Okay. So therefore now if you pick any point on this line segment, then the corresponding point on the function will be that point only. Okay, because this line segment is lying exactly on this line here. So therefore this is also convex function, because that point on the line segment will not be going below the corresponding point on the function, because that point is the same. Both of these 2 points C and D will be the same here. So suppose if this is C, so this is also the point D here. Okay, so therefore this is also a convex function. Okay, there is something called concave function. So in the concave function, what we see here is that again we pick any two arbitrary points on that function. If the line segment joining those two arbitrary points never goes above the corresponding point on the function. Okay. So an example of a concave function is zx equal to minus x square. So, this is something the function for zx equal to minus x square. So, this is kind of the mirror image of zx equal to x square around this x axis. So, if you will pick any line segment here on connecting any arbitrary points on this function, then any point on this line segment, suppose C, will never lie above the corresponding point on the function itself. Okay. Now, you can see that this function zx equal to x square is a convex function, but it is not a concave function. Similarly, zx equal to e to the power x is a convex function, but it is not a concave function. But this function zx equal to 2x plus 3, this is unique, because this is a convex function also, but it is a concave function also. Because again, when you will be picking any two arbitrary points here, A and B here, and you draw a line segment connecting those two. So, since any point on this line segment, suppose C, is not going above the corresponding point, because that point will also be the same, C and D will be the same, and therefore, both of these 2 points C and D are exactly the same, and therefore, it will satisfy this condition that this function will be concave function. So, this is a linear function. So, this is both convex and concave, whereas this is only a convex function and this is only a convex function. Okay. So, we will be continuing this discussion related to these convex functions and so on in the next lecture. Thank you.